Hello everybody. So welcome to this presentation of the new Saflager SH-45. We are here in Rimini in Beer Attraction. Very nice trade show. So this is the official launch of the new yeast. Okay. So we'll make a brief introduction. I'm going to show the SH-45 versus the rest of the range for the Saflager. And then we'll have the beautiful part of the biotransformation potential of that yeast, then some conclusion. All right, so let's go for the introduction. So I always like to introduce the yeast like this. So for me, what is really differentiating an ale from a lager is the species of yeast, okay? Ale is fermented with Cerevisiae, when lager is fermented with Saccharomyces pastorianus. And of course, you have the beautiful story about the bottom and top fermentation. So why do we call them like this? Let's picture ourselves 400 years ago, 500 years ago in a brewery, and they had open fermenters, okay? And without knowing what they were collecting, they were taking the foam at the end of fermentation and put it into the next fermenter. And by that, they selected a specific behavior that we name a phenotype of a yeast that would rise in the top of the fermenter at the end of fermentation. And then with the Industrial Revolution and the start of using of Pastorianus, the fermenter went vertical. They put a lid on top to protect from the contamination, and they needed a new behavior, a yeast that would sediment down in the bottom of the tank at the end of fermentation. And this is where the world's bottom fermentation comes from. And of course, you know that lager yeast have the ability to ferment at a lower temperature. So most of the time you're going to find 11, 12, 13, 14 degrees Celsius in the breweries, when ale is much higher. So what is Saccharomyces pastorianus? And the answer is really simple. It's an interspecies hybrid. So here in this audience, or also in the live stream, we are all hybrids of our parents. Okay, but this is called intra-species hybrids. Okay, we are a hybrid from the same species. Here is two different species that gave the birth to Pastorianus. The first parent is Cerevisiae. Cerevisiae is present everywhere on Earth. And the other parents, 50% of the DNA comes from Saccharomyces eubayanus. And the first time it was discovered was in Patagonia. Okay. So what happened? These two yeasts had an offspring, a natural hybridization, and most probably, and of course we don't know exactly, it occurred in a brewery environment. Why is that? Because you need to have the selection, the pressure of selection, which is the cold environment. Well, it's possible that was somewhere in Germany in basement fermentation that this hybrid was born. And something is not appearing on the screen. Yes, it is. And the abilities is, of course, the ability to ferment at low temperature, maltotriose positive, POF negative, high sedimentation. These are the main characteristics. And also very interesting for the lab, millibiose positive. There is no millibiose in the world, but very easy to recognize a Pastorianus versus a Cerevisiae in the lab because of that shoe. So this is the range. So SH-45 is now the fifth yeast in the range. And here they are classified according to the aromatic profile, fermentative profile. Okay? Very famous 3470 is neutral. Of course, I don't like neutral because it's fermentative neutral. But you put the yeast in the wort and it removes all the aldehydes. It increases the drinkability. It increases the freshness. So it's not neutral for the fermentation, but in terms of aromas of fermentation, it's quite neutral. And then you have the order of fruitiness. All these ones are going to be from no fruity estery to medium-high fruity estery. And of course, SH-45 is going to be medium-low fruity estery, but with the ability to make biotransformation with the Thiols, and we'll see that in a moment. So, the SH-45 versus the rest of the Saflager ranges. All right, so we made experimental conditions. This is development of the yeast, so it's not the baseline yet. So it was in a 50 liters laboratory environment, but it's exactly the same condition as the baseline. So as soon as we have the actual baseline, we will update and have more precise data. So it's 15 plate of wort, 100 gram per hectoliter, fairly classical, and 14 degrees Celsius fermentation. All right. So fermentation kinetics. You can see here we're all starting from the same point, and we have a yeast that's pretty fast, a yeast that's fairly slower, and the green line here is SH-45. Okay, and you can see it's an average fermentation speed. But what we found out in all of the trials we have made is that they all finish around the same time. So whatever fast start, slow start, it finishes at the same time. And in here we were finished by day 8, day 9. Okay, so quite a standard for 14 degrees Celsius lager fermentation. In terms of attenuation, of course, attenuation fermentation yield is linked to the wort. And we can see that they are all around the same level. In here, 3470 performing a little bit higher, but if you look at the scale, we start from 70 to 90, so it's really zoomed in, so you can see. And SH-45 is right in the middle of this, okay? So we have exactly what we expect from a lager. It's around 82, 83 in terms of attenuation yield. In terms of ester production, I'm going to talk in other units, okay? And other units is very simple. It's a way to compare different compounds together, because every single compound has a different perception threshold, okay? Perception threshold is the amount around which half of the population will detect. So if you are exactly the same concentration than the threshold, you are a 1. One other unit. If you are 2 times higher, you are 2, and etc., etc. So we see that E30 is quite high in terms of isoamyl acetate, the banana esters, which is the goal that used to be fruity estery, and SH-45 is, around 1.4, 1.5-ish. Okay, so not very expressive in terms of esters, but a bit more than the other ones. And of course, that's really nice for the lager fermentation. You have a bit of ester for the character of the beer, but we'll see that this yeast does much more afterwards. Okay, and this is the first development trial. So this is not the beer that we have at the booth today. It's another one that was made within a partner of Fermentis, quite close to the baseline, but we had dry hopping during fermentation. Why? During fermentation, we want to have direct contact between the hop and the yeast to have the biotransformation. So Citro, Amarillo, and Alerto Blanc, and you will see that this makes a lot of sense. You will see that later on. And what we found out is that we have the freshness of the lager, we have the citrus tropical coming from those very nice hops, and we have Thiolic, it's a green vegetal. I can also add also Sauvignon-like, that is coming from the biotransformation. And with the other ones that is not displayed here, you don't have that specific character of the biotransformation. So let's have a look at the biotransformation, okay? So in the hop, you have 3 compounds, and you have some potentials. You have some thiols, and you have some terpenes. Okay, terpenes are more floral, thiols are more on the fruity side. So we'll go essentially on the thiol side. So what happens? In the hop, you have some precursors, okay? And they are linked to another compound. So when they are linked, for example, to a cysteine or to the glutathione, you cannot perceive it, okay? You can have like, I don't know, strange amount of quantity of these, and you don't feel it at all. But thanks to certain yeast, you can break that bond and have the thiol that is freed. And then all of a sudden you get very nice aroma out of your hop that you didn't have before. Okay, so in the study that we made for the development, we have 6 different molecules. Okay, they're all in pairs. So this is 3-sulfanyl-hexanol. You don't have to remember it's and 3-sulfanyl-hexylacetate. The only difference between the two is the group alcohol and the group acetate. Okay, and just this little change will have massive impact on the flavor. So if you look at the threshold, this is 55 nanogram per liter, and this is 5. So it's 10 times less. So you need 10 times less to be able to perceive this flavor in the beer. So what is 5 nanogram per hectoliter? It's like, let's have a scale to be able to try to understand what it is. So I'll take the example of phenols. Phenols are very known for the 4-vinyl guaiacol, for example, for 4-vinyl phenol. It's 300 ppb or microgram per liter. Okay, so it represents around 6 drops of water in 1,000 liters. Okay, but this is another scale. If we go to 500 nanogram, 5 nanograms, so 5 ppt, it's like 6 drops of water in an Olympic swimming pool. And to be honest, it's not an Olympic swimming pool. It's 1.5 Olympic swimming pool. I didn't see myself dividing and put it in half of a swimming pool. No, it's extremely low. Like the amount that you need, and the detection is really hard to analyze as well because it's so low. The impact is really, really great. So let's have a look at some metabolic pathways. We have here the production of acetate esters, the fruity esters, isoamyl acetate, banana, from fusel alcohol and acetyl-CoA. Okay. Here, if we talk about the thiol precursors, the yeast is able to uptake it, and with the help of some enzyme, release some free thiols. Okay, so this is the first step. And you have here the 3-sulfanyl-hexanol, which has the grapefruit potential. Very, very nice flavor. And the yeast can go one step further. The yeast can use also the acetyl-CoA to make an esterification. Here you have the esters that is only at 5 ppt, and it will also be released on the media. And this is one that is very, very important with that yeast. So in the development of this yeast, we went to a partner lab, which is the University of Louvain-la-Neuve in Belgium. And what they did is they made some fermentation in lab scale with synthetic thiols. So the precursors were put in the wort without any hop. And then we saw what the fermentation would do. And at the end, they collected the beers and they extracted the thiol in a very specific methodology, and then they could analyze the samples. Okay? So here we have the results for 2 different types of thiols. The cysteine on top and the glutathione on the bottom. Okay? And the affinity of each yeast to each thiol is different. For example, K97 is quite good to release 3-sulfanyl-hexanol. It's the best amongst all the yeast. But if we look at here in the bottom, we have better potential to release glutathione thiols by E30 and SH-45. And this is the important part. This part in light yellow is the ester, the 3-sulfanyl-hexylacetate. And you can see that by far, SH-45 is the one that is releasing the highest amount. Okay, I know the scale is from 0 to 0.2, but believe me, it's enough, and I'll show you why. Okay, these are analyses of actual hops, and you have here what is already free in the hop, and what is the potential, and this is all in other units. Okay, what I showed you before. So if we look at here, Citra has already a lot of free thiols, and we know that's why this hop is so used in the brewing industry. Alerto Blanc has a bit of free thiols, and pretty much the other ones don't have. They're very nice aromas, of course, but they don't have the potential. And if you look here, let's say, for example, Polaris has a 2,800 other unit potential. So the release is very, very small, but there's so much of the precursors compared to what you need that you have an actual impact on the final beer. And we have here some example of very nice hops that have the potential: Sorachi, Amarillo, Polaris, and also Citra. Okay. So based on this, based on the release, Thiol, and on the other units, we're able to calculate, let's say, the maximum amount of other unit you can get out of those hops. Okay? So let's have a look. Here we are with Citra. 400 grams per hectoliter, which is fairly small compared to nowadays standard. And you have here in yellow what is already free and what is released and esterified by the yeast. Okay? So you have here trisulfanyl hexanol, passion fruit, grapefruit, and you have here trisulfanyl hexyl acetate, passion fruit, box tree, in other words, Sauvignon-like flavor. And you can see that, yes, Citra is already releasing a lot in the media, on theory, but SH-45 will be adding a quite significant amount of this compound. Okay? And this is not taking into account whatever is going to be stripped out by the CO2, because some of the flavor you lose during fermentation. For Alerto Blanc, we have less free thiols, but we still have a good potential. Oh, sorry, I'll go back. Here we go up to 50 in other units. You will not get 50 other units, of course. This is purely theoretical, but it will be enough for you to have this really nice feeling in the final beer. Here we are more around 20 extra other units coming in the potential from the yeast with Alerto Blanc, which is quite interesting as well, because here you don't have that much free already in the hop, and so you can really completely transform the way you perceive the beer thanks to the biotransformation potential of the yeast. And last, Amarillo. Amarillo had no free thiols, and you can see well, the potential is a bit lower, that we are around 8, 9 in other units, still at the 400 gram per hectoliter. So even with less precursors in the hop, you have quite good potential. So almost to the end of the presentation, the key learnings. So SH-45 is going to be a very, very nice lager. It ferments quite well at 14 degrees Celsius. We have an average attenuation 80, 82, very classical. It will produce a medium fruity estery character, but it has a significant action on the release and esterification of the glutathione thiols. And we have a treat for you. We have a beer that has been done by Birrificio Amerino. Yes, that we'll be able to taste in a second. And here is just the recipe, and we have quite good, normal mashing procedure, quite classical for a lager fermentation temperature from 13 to 14, and then diacetyl rest at 16 degrees Celsius. And hop was added during fermentation for the direct contact, around 50% of the fermentation. We're using Citra, Talus, and Equinox. So we recognize Citra with a nice potential for the thiols. And so in conclusion, we have a very classical lager fermentation. Fermentation speed and attenuation were really good. We demonstrated a very good ability of SH-45 to release thiols, especially from glutathione-related additives or precursors, to the contrary to the Saflager range and K97. And we have a lot of biotransformation potential, so we have really something that can help you to better use the hop, or maybe to use a bit less hop that you would have needed otherwise. and we have a very good esterification potential of the glutathione thiols to bring even more flavor to the beer. So a quick thank you for the Université Catholique de Louvain, PhD student Romain, Christians, and also Professor Sonia Collin. So please, now the floor is open for questions. If you have any questions, now is the time. Okay, so apparently there is no question, so thank you very much for your kind attention. Okay, and now just specifically for you, we have Francesco from Birrificio Amerino that will also talk, but in Italian about these. It's good? You have one question? Okay, sorry, we have one question, so...
There's a question online about if there will be small packages for home brewers.
Yes, so the question is there's going to be some small packages from home brewers? And the answer is yes. When we release classical yeast, it goes from the smaller package to the bigger package, so of course it's going to be available for everyone. All right, up to you now. Did you put it on? Need to...